So we're going to continue with chapter 10, which deals with now comparing two means. So as you can kind of have an idea of where we were going, in the first section here, we were comparing two proportions, and we were looking at that relationship. And now we're going to be comparing two means and looking at the relationship that exists there. So similar to what we saw in the last section in the last chapter, a lot of this stuff will look familiar to you. We're just dealing with two proportions, or two means rather, and two samples as opposed to one. So now, for example, we're saying, okay, let's compare the average amount of shoes a female owns compared to a male. Okay, so we're taking two distinct samples here, and we're comparing the means there. We can look at the sampling distribution between those means. We can look at a confidence interval between those means, the difference of those means, and we can look at a significance test for the difference of the means. Sort of similar to what we saw with a paired test, but a paired test, remember, was one single sample, and we're looking at the pair. Here we have two distinct samples when we're talking about that. So the sampling distribution for the difference of means describes the possible values of x1 bar minus x2 bar and how often they occur. Okay, so that's what we're dealing with, is what is the difference between those two means, and how often do those differences occur? The shape of the sampling distribution of the difference of means for all those mean problems, we still have that same idea here. So the shape is approximately normal, and now we're back to means. So we can either use the central limit theorem, where our sample size has to be greater than or equal to 30, must be true for both of the samples, or the populations are normal. The mean, or the center of the sampling distribution, is just equal to the sample means, or the population means, I should say. And here's your formula for the standard deviation of the sampling distribution for the difference of means. So it's the square root. Now remember, if it was just a single one, we would just have sigma over the square root of n. Here, when we're combining standard deviations back to way in the beginning of the year, remember we square them and we add them. It's the same idea here for this formula. And these are not formulas you need to memorize. Keep in mind, they're on the formula sheet. If we go to sampling distributions and sampling distributions for means, we're talking about two population means. Here's the mean of the sampling distribution. Here's the standard deviation of the sampling distribution. And we're going to see here's the standard error of the sampling distribution. So they're not formulas that you need to memorize. They are on the formula sheet. Just use them there. 10% condition, that 10% independence condition, does need to be met to use that standard deviation formula. The graph that's shown here is just the idea, again, of the sampling distribution. Notice that the shape is approximately normal here. It's that bell-shaped curve that we've been dealing with. We know that the mean, it's going to be centered at what that population mean for the first one minus the second one is, and the standard deviation formula that we just saw up above. We'll look at this example related to potato chips in class. Now let's talk about the significance tests and confidence intervals for means. So I've written over here what your general null and alternative hypotheses are going to look like for significance tests for the difference in means. I want to make sure that you're aware. Notice when we did paired t-tests, we were talking about the mean difference. What is the average difference? Here, we're talking about the difference of the means, hence the difference between those two problems, or those two scenarios. So your null hypothesis is going to be that the first mean is equal to the second mean. For example, the actual average number of shoes a female owns is equal to the actual, or the true mean for males. And then my alternative, same idea. I have three options. I have my two one-sided test options for greater than or less than, and then I have my two-sided test for not equal to. So am I trying to prove that the true mean for females is greater than males, less than males, not equal to males, whatever it might be? Okay, the same concept as we saw when we were doing a single or a one sample test for means. Here's your standard error formula. Again, it's the only difference between the standard error formula and the standard deviation formula is that we're using sample standard deviations here, and that formula is also on the formula sheet right there. So it's not something that you need to memorize. Okay, those formulas are on the formula sheet. I've shown you the t-test statistic, or your t-score here, by hand. I do not recommend that you do these problems by hand. Okay, it's even rare that you would see something like this as a multiple choice question, but I do want you to be aware of that formula. Again, it's statistic minus parameter over the standard error. Really, all you're doing is subtracting your sample means, and you're putting it over the standard error formula, because you're subtracting 0 because you're assuming that there's no difference, which is what your null hypothesis says. So That t-score or t-test statistic measures how many standard errors our sample difference is from the null hypothesis, which is assumed to be 0. Conditions, same conditions that we just saw, okay? Random sample or random assignment, meaning a random experiment has been performed. Your normality condition, we're talking about means. So we have our central limit theorem. Both our sample sizes, both of them have to be greater than or equal to 30. If that's not true, then both populations being normal. If that's not true, then we have to graph both of our sample sets of data and show that there's no obvious skewness or outliers. We also have our 10% independence condition. That condition, like usual, is only for random sampling. If we're doing a randomized experiment or using random assignment, we don't check the independence condition. The distribution that the two-sample t-statistic has is a t-distribution with degrees of freedom that's difficult to calculate by hand. So we're going to use the calculator to do all of our tests here, and we're going to be running a two-sample t-test. So if we go on our calculators and we go over to stat and over to test, we'll be running a two-sample t-test for all these. Notice that there is a two-sample z-test, that is for means. That would be in the very, very rare, aka not going to happen case, where they give you the population standard deviation. So we'll be running two-sample t-tests when we're doing these. Like usual, you can have raw data to put in or stats. We'll talk about the different things that you can plug in, but the calculator will give you the degrees of freedom to use. As I said before, we're using a t-statistic rather than a z-statistic because the same reason as we saw in the last chapter. We're not going to know the population standard deviation sigma. So we're using the sample standard deviations, which have more variability, which the t-distribution has. Hence why we'll be using a t-test to be running as opposed to a z-test. As I said before, we'll be using technology to find the degrees of freedom. And for mean problems, we do not use the pooled option. It will ask you pooled or not pooled. We are not pooling for means. Give you a second to catch your breath. I know I've said a lot. So on the calculator, okay, for example, say we went out, we got our sample mean for the number of shoes you own. For the females, they own on average 21.5 shoes, and maybe their standard deviation is 4.5, and maybe we took a sample of 32 people. And then maybe for the males, they own an average of 16 shoes with a standard deviation of 6.3 and a sample size of 40. Your sample sizes don't have to be equal, okay? So just be aware of that. And maybe we think that on average, females own more shoes than males. So we're going to pick the greater than. Mu sub 1 is greater than mu sub 2. You do not choose the pooled option. And like usual, you can see a picture if you want, or you can go to calculate. I'll just go to calculate. There's my sample, or sorry, there's my test statistic. There's my p-value, like I would compare to my significance level like normal. And here is the degrees of freedom that the calculator's gotten for us. And again, we don't need to know how to do that by hand. The calculator can get those degrees of freedom for us, but it is important that you always write down the degrees of freedom when you're doing this type of problem. So in this case, like normal, we would reject the null hypothesis here. P-value is low, it's almost 0. And therefore, we would have convincing evidence that on average, females own more shoes than males, or the true mean number of shoes owned for females is greater than the mean number for males, something like that. Okay? But run the test on the calculator. Two-sample t-test, absolutely do it on the calculator. Use it all the time. If not, you'd have to go through that same process. Use that ugly test statistic formula. Look it up in the table or use TCDF, and it's just not worth it to do that. Okay, so yes, use it all the time. Stat test, two-sample t-test, which is number 4 on the calculator. Highly recommend that you do that. All right, let's talk about confidence intervals for the difference of means now. So the formula for a two-sample confidence interval for mean is shown to you right here. You're going to take your sample means and subtract them plus or minus the t critical value times that standard error formula that we saw before. Once again, I suggest that you do it on the calculator, but you might see a multiple choice question on the AP exam or on one of our tests where you'll need to apply the formula. Conditions, same conditions that we've seen for all these mean problems that we just saw for the significance test. Random sample or random assignment / an experiment. Normality condition, both your sample sizes are greater than or equal to 30 because we're dealing with means, so we can use the central limit theorem. We can graph the sample data or the populations are normal. And then your independence condition, only when you're doing random sampling. Both of your sample sizes are less than 10% of the population size. As I said before, you never pool for mean problems. That assumes that the standard deviations for the populations in both your sample or both your populations are equal to one another, and that's just not realistic. So we do not pool for means, okay? We pooled in proportion problems because we assumed that they were equal. This is really beyond the scope of the course going into pooling, okay? It's something that you might learn about if you take a kind of second level or even third level statistics course, but it's beyond the scope of this course. All you need to know is that you do not pool for mean problems. It'll always ask you, if we go to stat, over to tests, and either if we're running a 2-sample t-test, or which we'll be doing here, a 2-sample t-interval, okay, it's going to ask you if you're going to pool the data, and you always want to make sure you're not pooling for mean problems. And what we're creating here is we're creating a confidence interval for what we think the true mean difference is between whatever we're talking about. So if we think back to our shoes example that we were dealing with, we're looking at what is the true mean difference in shoes that females own and males own. So if I kind of look at that and use that same data that we just had, sample mean for the females 21.5 with this standard deviation, the sample size, and so on for the males, and I create that confidence interval, this is what I'm 95% confident that the actual mean difference in the number of shoes females own compared to males is between 2.12 and 8.88. So I'm 95% sure that on average, females own somewhere between 2 and 2.12 and 8.88 shoes more than males. And that's what that confidence interval is for, the difference of means. And again, use the calculator, 2-sample t-interval, no reason to do it by hand. Okay, use the calculator. We'll go through this chocolate chip example in class. Last page in the notes here. Okay, should you use 2-sample t procedures with t paired data or with paired data? Why not? How can you know which procedure to use? So this is what I kind of hinted at earlier in the class. Okay, a 2-sample t test or t interval. The order of the data doesn't matter. We've taken 2 distinct independent samples and we're looking at the difference of the means, okay? We're looking at the difference between our 2 means. There's not really a relationship between those 2 samples. In a paired t-interval, the order matters. I have to make sure I've correctly ordered each of my pairs, okay? And the order matters. I'm doing this one thing one way and then another way. There's a relationship between my samples and I'm looking at the mean difference, okay? So 2-sample t, you want to think distinct samples. There's not really a relationship there where for each individual pair it matters. Paired t, you want to think more one sample and the order of the values matter. We're looking for the mean difference. We'll look at an example here and how we can do it 2 different ways in class. I will see you then where we'll go through plenty of examples for running 2-sample t tests, intervals, and sampling distributions. See you then.